Welcome to this year's Brown Bag series. This is the first one this year, first of hopefully many now that we're out of COVID. Laura will be presenting today on the geology and geography around Santa Fe, and this is a broad Santa Fe. You've all been asking great questions already, so thank you. Feel free to continue to ask questions. And Laura, do you want people to ask questions during the talk or at the end?
During the talk, I think is fine because we have a smaller group.
Sounds
But
good.
make them significant questions, I guess, because we want to keep the flow moving.
Sounds good. This will be available as a recording when we're done with this on the FOA Facebook page. So you'll be able to watch it again, but the recording will not be distributed. It will just be posted on that page. So it's all yours, Laura. Take it away.
All right. Thank you, Shelby. Welcome everyone today to learn a little bit about the geology around the Santa Fe area. So today's brown bag discussion is entitled Roadside Geology and Geography Around Santa Fe. So as you drive around in your car and see the different landforms, that's what we're going to be talking about. My name is Laura Reich. I'm a retired geoscientist, and I'm also a volunteer at the Office of Archaeological Studies on the western side of Santa Fe. So who am I? I'm originally from Wisconsin. I am an NFL owner. That means I own a share of the Green Bay Packers. I'm a cheesehead. Yeah, my email's cheesehead. You'll see that at the end. And I got my bachelor's degree in geology and my master's degree in geophysics from the University of Wisconsin at Milwaukee. And I was recruited from there to work for Amoco Production Company down in Houston, Texas. So I did my career in Houston for about 26 years, worked half my time domestic, half the time international, retired here in Santa Fe. And I do a bunch of volunteer work. So I started out at Pecos National Historical Park in the visitor center, learning everything about the park. Then I developed their geology program, and we have a little bit on the website there. And then I do monthly tours that you can see on their website. I volunteer here in the Archaeomagnetic Laboratory and the Carbon-14 Laboratory doing age dating. I do very minor stuff. I'm like a technician, I guess. Recently started with the Cancer Foundation for New Mexico, where I'm kind of a candy striper there. So that's a non-scientific thing. And then we have a social group in town called Lesgo, New Mexico. So I'm one of the leaders with that. So I do a lot of volunteer work here in my retirement. So here's the outline for today's talk and discussion. So I'm going to give you a quick crash course on the introduction of geology, like Geology 100 from the university. And just so we're all kind of thinking like geologists. And we'll look a little bit at the landforms. And then I'm going to go through all the things you can see from your car window. And I'll usually start with a photograph. Then I'll get into the geologic description. And we're going to go from oldest to youngest. So we're going to start with the Rocky Mountains, because those rocks there are about 1.5 billion or 1.6 billion years old. They're super old. And then we're going to end up right here where we're sitting in the Caja del Rio, which are some of the youngest rocks in this area. So start here with a little bit of history. And everything I show is public domain. This is from the internet. And these maps are from the 1850s. So in the 1820s and 1830s in the Ortiz and San Pedro Mountains, gold was discovered. So the oldest gold mines in this part of the world, people think probably are California, but they're really here in New Mexico. And the problem was, like the problems we have nowadays, not enough water. So eventually they moved on to California area and Colorado. And as the West was expanding, we needed to make maps for the military reasons and for railroad and other reasons. So that was the nature behind most of these maps. So the very first geologic map there is at the top. And on my maps, I usually have a yellow star for Santa Fe. So this is the Santa Fe up here at the top. And then these are the Rocky Mountains here, kind of in this reddish color. And you'll notice the Valles Caldera here is just this big blob, but they did notice it's something different geological. And so this map kind of runs east to west. Here's Zuni area, Zuni Pueblo on the western part of New Mexico, which if you come down to this lower map here, this map maps the Grand Canyon, and Zuni's on the east part of that. So these are very early geological maps, like I said, for military and expansion reasons. And then I just like to show people this map because this is what New Mexico looked like back in the late 1850s. Thank you. Yeah, should have done that to begin with. Turned off the lights. So here's Santa Fe. So, New Mexico now is kind of north-south here, but in the past, New Mexico was the lion's share of the New Mexico territory. And then here's Arizona down here in the south. So it looks a little different than today. And I want to point out the most significant geologic feature we have is kind of a negative feature in the state. It's the Rio Grande River. And so it bisects the state more or less in half here. And then we're here, the yellow star, and this red arrow is Albuquerque. And then on the bottom is a profile going from the north part of the state to the southern part of the state. So you can see up north here how steep it is, up here in the Taos type area. Here's Albuquerque annotated, and then it's kind of just a gradual decline all the way down. So that's our largest geologic feature. It's 475 miles long in New Mexico, and that's about half the length of the entire river. The river starts up in southern Colorado around Creed, and then goes to Seminole Canyon in Texas, to the Rio Grande River. The Gulf Coast. I'm getting confused with my Pecos talk. Pecos River meets at Seminole Canyon in Texas. And then there's quite a bit of elevation drop too there, almost 4,000 feet. So it probably doesn't really mean anything, but I think it's interesting. Albuquerque is about 1/3 the distance. So that's our greatest geologic feature. So now we're going to get into some basic geology. How many of y'all took geology classes in high school or college? So we have a few people here a little bit knowledgeable on geology. So hopefully this is a good refresher for you. So geology is the study of the earth. That encompasses a lot of things. It's not the study of rocks, it's the study of the earth. So it includes everything really. And then I like to ask people, what's the difference between a mineral and a rock? So how I describe it, it's like making a chocolate chip cookie. So the sediments are the sugar, the flour, the chocolate chips, the nuts, etc. You stir them all together and you add in a little butter and liquid and you press them. That's kind of a sedimentary rock. Well, you put them in the oven and you heat them. It changes. That's a metamorphic rock. And if you burn them, they melt and they're black. They're an igneous rock. So right there, you have the rock cycle in a chocolate chip cookie. And that's what this is showing here. We can start, let's just say rocks are started through volcanic activity. So you can have igneous rocks at the surface like volcanoes, or sometimes you have these things called batholiths, which are in the subsurface. Then they erode and you get sediments along the way and in the water. They get buried, compressed, they turn into sedimentary rocks. They get buried so deep, they get kind of partially melted. So you get a metamorphic rock through heat or sometimes tectonic pressure. So a change in pressure and heat, you get a metamorphic rock. And then sometimes they get so darn hot, they got to kind of float right on up to the top. So there's your cycle. Does that make sense to everyone? Oh, and like everything in life, we have to have a few key principles or laws that we follow. So here's some geologic principles. So big word, uniformitarianism. It's kind of obvious when you read it maybe, but that's an old principle. The key to the present is the key to the past. So if you see a beach today, like I'm from Houston, go to Galveston, you see a beach, you pick up a rock, you're like, oh, that kind of looks like a beach. Well, voila, it was a beach. It's not necessarily that hard. So what you see today is kind of what happened in the past. The law of original horizontality, sediments are deposited in a horizontal way. So we just make this assumptions that these rock units are horizontal when we see them out in the wild. So here you see all the sedimentary layers, they're horizontal. Then there's the law of superposition, which says the oldest rocks generally are on the bottom. That makes sense that they have to go where there's open space, they're on the bottom. Now you start adding in plate tectonics and structure, things will change, but these are just simple guidelines. The law of cross-cutting relationships. So rock layers are in place before they're faulted or shifted. So here's like, just assume this is some magma coming up through a chamber, or you could picture it as a fault. It cross-cuts these pre-existing layers. So that's the law of cross-cutting relationships. And then Walther's law, this is a little bit more technical, but layers that you see will be laterally consistent, and they also change as you go up horizontally. So what this says is, like, if I saw a beach here, I would later on see the beach higher in the section. This diagram doesn't show it very well, but stratigraphic layers are laterally and vertically related. So let's talk about the Earth now for a minute or so. So this diagram is great. So the Earth is made up of an inner core, which is solid iron and nickel. Then there's an outer core, which is liquid iron and nickel. So that's highly dense stuff. Then there's the mantle, which is liquid rock, and it's not very liquid. It has like 1% water, but it's just enough. It would be like a super viscous type hard gel almost. Then here at the surface, we have continental crust and oceanic crust in blue. Continental crust tends to be the lighter colors, the pinks and the whites and the grays. It's got a lower density and it's usually fairly thick, like our mountains, they're fairly thick. Oceanic crust here, which on this diagram is shown in blue, is a thin layer and it's highly dense. It's got a lot more metallic minerals in it. So when two of these plates come together, we have oceanic plates in blue and continental plates in brown. When they come together, if it's an oceanic plate, it'll actually, because it's thin and heavy, it'll be subducted underneath the continental plate. And this is going to be important when we look at our Rio Grande Rift. And this diagram doesn't have it, but if you think of the Himalayas, when two continents come together, they're big and blocky, there's nowhere to go, so they just buckle up and make mountains. So when you look at a map of the world, most of the mountains are on the edges of continents because it's from these plates bumping together. So these plates are kind of just floating around on top of, the asthenosphere, which is the light green, and then the mantle here. And a little fact I learned in college is every time you clip your nails, I clip my nails once a week or maybe twice a week. That's about as fast as how fast the Pacific plate is moving. So these plates can move fairly fast in geologic time, but of course in human time, I can't watch my fingernail grow, can I? I just know when I need to cut it. And that's how fast. So every time I cut my fingernails, I'm like, wow, the Pacific plate just moved another couple millimeters. Now we'll talk about sedimentary rock. So this is a block diagram, a 3D diagram. And up here at the top are the mountains, and out here is the ocean in blue. And so this talks about the different types of depositional environments where you get different kinds of sediments that have eroded off the mountains. So terrestrial will be labeled here in red. Terrestrial is a big name for land. Transitional just means in between, and then marine is blue. So we typically have terrestrial and marine type sediments. So terrestrial are on the land. So in the mountains here, you can have alluvial fans. Like if you go down to Albuquerque and you go to the volcanoes or something, Bernalillo, and then you're driving towards the Sandias, you kind of see these big aprons of sediments. Those are alluvial fans. Death Valley is a classic example, but I think the Albuquerque Basin is quite good too. And then they lead into rivers and arroyos and all that. So you get fluvial deposits, which means rivers. So you get fluvial and deltaic. So there's a lot of those here. So when you have mountains, there's alluvial fans, there's rivers, there's all that erosional stuff coming off of them from the rain, the snow, etc., maybe even the wind. Then you get out in the flattish area in front of the mountains and you start getting sand dunes and just kind of clay and stuff blowing around and lacustrine, so shallow lake beds. And then there's this transitional zone, which is maybe sometimes our favorite zone because it's the beach. So that's where the little tiki bars are here, right in the transition. And then you get into the shallow marine where you have reefs and things like that, clams, fossils. Then you go off into the very deep water, and then there's big sedimentary deposits in the deep ocean too. So let's talk a little bit about paleogeography. So paleo means old, the old geography. So scientists have researched all this, and this is how they think that the Western United States looked back around 290 million years ago down here. We're going to be talking about the ancestral Rockies. So about 290 million, 300 years ago, the star, that's us, New Mexico, was at the equator. So you guys have heard about Pangea, the supercontinent. So that's when all the continents came together. So generally in the Northern Hemisphere, we call those Laurasia, Laurussia, different names. And in the Southern Hemisphere, where Africa and South America, Gondwana land. So they all came together. And here's this big suture zone that came together. These are like the Himalayas from 300 million years ago of all these continents coming together. So this global map, that's the big picture. Now let's zoom to our area. So here's this big suture zone where all the continents are coming together. These are actually the Appalachians on the East Coast. So back in their day, they were as big as the Himalayas possibly. And even the Marathon area and all that in Central Texas. Well, here's the star, us. So we had some mountains here too that formed back then, 300 million years ago. We're kind of oriented a different way just because there were some different stress fields in play. But 300 million years ago, New Mexico's at the equator. We were these mountains, and it's kind of like an island, isn't it? So some of the rocks you see here in New Mexico, actually you'll see in Wyoming, Colorado, Utah, and all that around here. So we were equatorial, and we had some mountains. Those are called the ancestral Rockies. Then here, what formed the modern landscape? So we had those Rockies, they kind of disappeared. So here we are in the Cretaceous, 85 million years ago. And you've probably heard about the big Cretaceous seaways. If you go to anywhere, they talk about dinosaurs. This is a big thing. Dinosaurs roamed all over the place, but of course, like us, they like the beach too. So they were kind of along these margins. Here we are. New Mexico is a big dinosaur state. If you don't know that, that's something to dig into. We have a lot of great dinosaur stuff here. Kind of in the Northwest and the Northeast are the most popular areas in the Albuquerque area. So that's the Cretaceous Seaway. So you can see those mountains are gone, right? So now we jump over here. Here's the modern day Rockies. They were formed, the Laramide orogeny, 60 to 50 million years ago. So they started forming at the end of the Cretaceous. It kind of looks similar to what we have now. Then eventually we get to the more modern here. This is, I had to get the word Wisconsin in here in this talk because I'm from Wisconsin. So this is the Wisconsin Ice Age, which was the last ice age here in the United States. And so a lot of it was the continental sheets coming up there, the ice sheets coming off of Canada. But we had some mountain glaciers here too. And I don't know a lot about the mountain glaciers in New Mexico, but I think when you look at Wheeler Peak, maybe even our upper ski area, certainly the Truchas area, there were small little mountain glaciers there. This is one of my most favorite slides. This is from the New Mexico Bureau of Geology and Mineral Resources. So on the left side is paleolatitude. So again, it's just the old latitude of our continent. And across the top is the oldest geologic age coming here to the youngest geologic age. And then this red track is just the position of New Mexico, or really North America, through time. So let's start over here on the left, follow the dot. So we're in the Cambrian, about 550 million years ago. And this is where New Mexico was. It's about 10 degrees north of the equator at that time. About the same as modern day Caracas, Venezuela. So through plate tectonics, the continent is kind of trucking along, crosses the equator here around 500 million years ago in the Ordovician, goes all the way south down here to the modern day Rio de Janeiro, Brazil. That's around 400 million years ago, makes an abrupt change, zips back up towards the equator. And here's the Pangaea, the supercontinent, the ancestral Rockies, they formed around this time frame. We crossed the equator there about 300 million years ago in the Pennsylvania Permian. And then we kind of just keep zipping north the whole way with a few wobbles along. You know, we got as far north as Seattle. So see Seattle, and then came kind of down south to where we are now. So isn't that a really cool diagram? And you can find this on the internet. It's easy to find. And then you can see along the red path there, the different animals that kind of evolved through time. So it gives you a little bit of geologic history from the biological perspective. This is another great diagram out of the Smithsonian. So this is a stratigraphic column. So geologic age, stratigraphy, the oldest down here at the bottom. And so on the right-hand side are layers, and these things are not to scale. There's the age dates along on the far right. And then in the middle here, it's got little pictures of the types of animals or fossils you would find in those different layers. So the main parts of the geologic age are the Archean, which is super duper old, then the Proterozoic. So you can see this is like 2.5 billion years just squished in that little part. Then we get into the parts of geology we maybe talk more about in Earth's history. Here's the Paleozoic. It means hidden life, old life. Mesozoic is middle life or the age of reptiles. And then Cenozoic is viewable life or the life of mammals. And then we have different eras and epochs, described here. So in this Pennsylvanian Permian, this is that time frame of the supercontinent. This is where we had Pangaea, and that's the age of our ancestral Rockies. Then all our dinosaurs are here in green. And then our modern day Rockies formed at the end of the Cretaceous up into the Paleocene, Eocene. So this is the age of our modern Rocky formations. And then a lot of activity happened here since then in the Cenozoic. So what I've done on the right here, I've annotated. So our oldest rocks, which are about 1.6 or 7 billion years old, they formed beneath the Earth's surface. And then we did have some mountains back in that Cambrian, PreCambrian, Proterozoic. They've eroded away. Then we had our ancestral Rockies. They rose up, they're thousands and thousands of feet, fully eroded away. And then now we have our modern day Rockies. And each one of those times, the rocks you see now that are 1.7 billion years old, they're the same rocks. They popped up, eroded, popped up, eroded. So there must have been a huge amount of those rocks in the subsurface, right? And it's that pink granite. It's a metamorphosed granite and sediments, and we call it a granitic gneiss. That's what you see around here. I just simply call it the pink granite, but it's actually so old that granite and the sediments that kind of sat in between the granites have been so heated and contorted through history and plate tectonics. The same rocks go up, erode, and now they're up for the third time. And now they're eroding too, but there's still some being building a little bit, but there's more erosion in place. Well, then what I have all here in red, this is a lot of the modern and mostly associated also with volcanics. So geologically, very interesting place. So now let me get a little bit big picture here. This is a physiographic map of the Four Corners region. And so if you were to scrape off all the vegetation and the soil, you would see the bedrock underneath. And that bedrock underpins kind of certain geologic styles, whether there's mountains, there's the Great Lakes, there's an ocean. Those things are changing based on the underlying geology that sometimes you see, but usually we don't because there's soils and grasses on top. So this is a physiographic map of the whole United States. And what I'm doing here is I'm zooming in on our map, the Four Corners area. So here's the Four Corners right in the center: Utah, Colorado, New Mexico, Arizona. And then here's our Rio Grande River in green, cutting our state in half. Star there for where Santa Fe is. And here I've noted the red, the Continental Divide, going right through the western part of New Mexico. So who's all been to Ghost Ranch? Who's all been to the Grand Canyon? Who thinks it's some of the prettiest rocks and places you've ever been on this earth? Well, it's the Colorado Plateau in blue here. So we got a good chunk of the Colorado Plateau here in New Mexico. So Ghost Ranch sits over here. And of course, the Grand Canyon's over there. This brown, these are Rocky Mountains. The light yellow, that's the kind of the grasslands and the high plains as you go towards Texas or Tucumcari or whatever. Amarillo gets super flat. And then this dark yellow, this is the basin and range, and that really plays into our Rio Grande Rift. It's most expressive, well, our rift is expressive, but really if you drive through Nevada and there's all those mountains and valleys, that's part of this basin and range area. So simply, I mean, we have a lot of diverse geology in our entire state, but look at Santa Fe is right here. So we're basically right. We got the Rio Grande Rift, the basin range here, the mountains to the north. Colorado Plateau is not very far away. I don't know how long it takes to get you have to go past Abiquiu. Abiquiu is still in the Rio Grande Rift, but I mean, we're an hour and a half or less away. And then the Great Plains, you're wrapping around Las Vegas. So you got a lot of geologic diversity very close to where we live. This is a state map. This just kind of simplifies the exact same thing. So this means Southern Rocky Mountains, Rio Grande Rift, the Mogollon Daytil volcanic field, and then the high plains. Oh, and then here's the basin range down here. The browns are the mountains. I like to show things several times so you have this imprinted in your mind. So now we're going to get into what we see around Santa Fe. So here's the Rio Grande River in yellow, us in the star, all these little red dots. That's what I'm going to show you. All of these things you can see driving around Santa Fe. So Jemez Mountains over here in the green, and you can see the Valles Caldera very well here. This is a 3D shaded relief map. Here's the Rocky Mountains over here. Sandia's down here. So here's a view if you're in the airplane. So we're down here by Albuquerque because here's Interstate 40 and we're looking north. These are the Sandia Mountains down here. We're looking north. Here's towards Santa Fe. Up here's the Colorado border. And I will say the San Luis Basin, which incorporates a lot of the Taos area and goes up to Salinas. It's the largest alpine valley in the world. Right here in our backyard. Isn't that cool? And of course, it's punctured by these volcanoes, so it's filled with a lot of volcanics.
So what does Alpine Valley mean? It's a certain altitude?
Yeah, and I don't know, I don't have that memorized, but it's above 7,000 or 8,000 feet. So it's the largest valley in the world above a certain elevation. And it is beautiful. If you haven't driven up there, take a road trip. It's really lovely. These are the areas we're going to take a look at now. Here's Santa Fe and the Star, but Sangre de Cristo Mountains, El Dorado, Galisteo, then a bunch of Rio Grande type stuff, Rio Grande Rift, Sandia Mountains, the San Pedro's Ortiz, Cerrillos Hills. And then over here, associated with the Jemez, you've got Valles Caldera, Bandelier, Tent Rocks, and lastly, the Caja del Rio, where we're sitting today. So this is a geologic map put out by the state. And the purples here are those super old rocks. the 1.8, 1.7, 1.6 billion year old granite type things that underpin all our Rocky Mountains. These cool colors, blue and green, those are sedimentary rocks. So layered rocks. This orange and pinkish color, these are volcanics. And if you see red somewhere else, those are volcanics. Then these lighter yellows, these are just modern deposits. And I did put this in here for fun. This is how the area was mapped in 1858. So a lot of changes. You know, in 1858, they only probably had two modes to do this. It was their own feet or horseback riding. So we have a lot more technology since then. All right, so let's start our looking at things as we drive around town. So here's a view of the foothills from I-25, kind of heading towards El Dorado, but you're on the south end, kind of there by St. Francis. These are those dinosaurs along Rabbit Road. So here you go. Here's the foothills of the Rocky Mountains. I took this winter. You can see all the snow. Been mentioning this, but it's granitic gneiss. So it's metamorphosed granite and sediments that are kind of all balled up. And there's a lot of lineations in there because there's been a lot of plate tectonics. And when you squeeze rocks, the minerals kind of line up. So a lot of times they'll be black and pink streaked. They're super hard. You might think they're sedimentary, but they're this kind of metamorphosed granite. And here's their age range from 2,500 to 530 million years ago. I use 1.5, 1.6 as a generic. So that's the southern terminus of the Rocky Mountains. Here's some more looks of it around town. So here I'm on Cerros Road, here by Seiler, driving towards. Here's the ski area up here and the aspens that don't have any leaves right now. But that's the core of the Sangre de Cristo Mountains. It's the southern range in the Rocky Mountains. If you drive between El Dorado and Santa Fe, I-25, there's all these road cuts. So you get this beautiful look at what the inside of the mountains look like. So granitic gneiss and metasediments, and it's kind of pink, and you'll see black streaks in there. And then here I was up towards Los Alamos looking across the way. So here's we have a flat basin, but then you have all these mountains behind there, and these snow peaks are generally 13,000 feet above sea level. So what form those? They sure are beautiful to look at and ski in and hike in. So these formed about 50 million years ago in what we call the Laramide orogeny. So over on the west coast, follow the red dot here on the top, California, we had an oceanic plate, the Pacific plate. So the skinny little thin heavy plate, it was subducted below the continental plates. So that's the oceanic plate, and here's the continental plate. So things started to buckle up, and then based on the physics going to the middle here, it goes underneath the mantle, and see the Rocky Mountains are starting to form because things are getting pushed and squeezed and buckled up. And then go down to this, the third thing on the bottom here on the orange pink. Then this oceanic plate, the Farallon plate, takes a deep dive and it brings in the asthenosphere, which is kind of some liquid molten. And that's when it starts cracking up and causing the volcanics in our part of the world. So basically, when you bend something, like if you were to take a metal rod and bend it, it gets tension and it gets those cracks on top. So in a way, it was bent from these plate tectonics coming from the west coast. It was bent, and then there was extra molten material below, and it made its way up. And so you started having volcanoes. And this all started happening, the mountains started forming kind of this 60 to 40 million years ago. But then about 35 million years ago, we started getting the magma reaching the surface. So it's kind of all one very large and slow process that first formed our mountains, then eventually formed the Rio Grande Rift. So now we'll move to El Dorado. So you form those mountains. So when mountains go up, a lot of times there's a low space in front of them. And those are the basins, and they catch the sediments that erode off the mountains. And that's what El Dorado is. It's a basin that is right next to the Rocky Mountains. And you can see that this is more modern material, but it's a lot of loose, unconsolidated material right here. So here I wrote that El Dorado is part of a foreland downward basin that formed while the Rocky Mountains were being uplifted. And locally, what I've shown here in the rocks, it's called the Ancha Formation. So here's some geologic maps from the state. Here, this big orange map. So the Rocky Mountains are in the purple. So somebody asked, where's the terminus? I think this is I-25 coming through here, this black line. So then you've got the Sunlit Hills, and a couple of the El Dorado Hills are still the granite from the Rocky Mountains. Then all this orange in front of that's all the sediment that's been shed off the Rocky Mountains. So that's a geologic map from the surface. Now, if you take a cross section B to B prime here, and you look up here, you like if you're cutting a trench through all this, here's the Rocky Mountains in the brown and the pink. Those are all those really super old igneous rocks. And then here's the sedimentary deposits in the Foreland Front Basin. And that's what underpins El Dorado. That's where El Dorado gets their groundwater from and everything. They have a lot of sediments they can drill into. Then if you look at the big picture here, here's the Rio Grande Rift, which is a series of basins that have connected up. And here's the Espanola Basin, which sits at the front of the mountains too. It just kind of wraps around. So El Dorado actually is part of the Espanola Basin. It's kind of like a little bit of an L. It just wraps around the front of the mountains. And we'll talk about the Albuquerque Basin soon. And there's where El Dorado is. So you can look at where you live, but all of El Dorado is in the orange. So here's the Galisteo Basin, just kind of moving further south. And these are all different rock units that shed off those ancestral Rocky Mountains. So this is what you would see that's underneath El Dorado where you live, because there's a lot of modern sediments in El Dorado, but if you drilled a well, you'd be drilling through these things here. If you haven't been to Galisteo Basin for hiking the preserve, it's fantastic. So here's this age, 55 to 35 million years ago. Again, the mountains were forming, 60 to 40 million years ago. Excuse me while I take a drink here. So a couple different formations, the Galisteo and the Diamond Tail. And they're mostly sandstones out there with different kinds of rock pebbles in them. You can find limestone, you can find granite, you can find some petrified wood. So I want to show the evolution here of the Galisteo Basin. So on the left is a geologic map that I showed you before. On the right is a Google Earth map. So here's the first animation. So there's a major fault that goes back to the Precambrian going from Tijeras to Cañoncito. It's a Cañoncito Tijeras, and it's kind of more of a transform fault where it's got strike slip motion in parallel versus down up. So you can see it connects a few of the features there. If you just see the, excuse me. If you see the, see how you go from Tijeras and then you got these are the Ortiz and all. They kind of connect up here to Cañoncito. And for the geologists, it's an old Grenville orogeny reactivated fault. But even if you just look on the color map, even if I was kind of just 10 years older, so I could almost see that's the edge of those colors, huh? So then here's the pink dotted line I put up here. You can see this is the western face of the Sandia Mountains and then the Rocky Mountains. So I just kind of drew those on there, copied them over here, and voila, they kind of match the colors. That makes sense. Then the blue line, there's nothing magical to this, but I saw some changes in geology. If you zoom in here, you see, I'm sorry about this. I got dust in my throat. So this is a type of transform that links the two mountains together. So they're offset by that 30 miles or so along the blue dashed line.
Do you think they were once in alignment?
No, because the Sandias, as we'll see, formed 10 million years ago. But geologically, there's always weaknesses that persist through time. Kind of like when you fix a crack in a house and it cracks again and it cracks again and it cracks again. So the earth has lines of weakness too. So they probably are related through these deep-seated weaknesses. So that's the formation. So you got the Albuquerque Basin we're going to talk about is down here, and then you got this Espanola Basin up here. And then the last thing I want to say is I put in these blue lines, and this is probably the old Santa Fe River or some version of that. And this is probably the Pecos River in olden times, 20, 30 million years ago. We had the Pecos River or whatever, it's pre-Pecos River actually flowing into the Galisteo and El Dorado areas. Through further uplift, they've kind of switched. So rivers switch through times too. It makes sense. Things get uplifted, volcanoes come, they got to go around them. So I just like to advertise my favorite hike in the Galisteo Basin. So I love Eliza's Ridge and Sphinx Loop. They're the most geologically interesting. These are actually Jurassic sandstones, the same sandstones, but they're very shortened here, but the same ones you see at Ghost Ranch. And then these rocks here are more modern. So those are Jurassic 160 million years ago. These are maybe just 20 or 30 million years ago. And they're sandstones that formed from eroding off the ancestral Rocky Mountains. So if you guys hiked out at the Galsdale Basin Preserve, they have the map I have inset down here on the bottom. You can find on their webpage. But Eliza's Ridge and Sphinx Loop are fantastic. Do them together, they're 5 miles. You do them independently, they're 2 or 3 miles each. So in El Dorado, if you go to one of those granitic hills, Trail 103, which is by 285 kind of, you can look southwest and you start to see a lot of things associated with the Rio Grande Rift. So that's where I'm standing. So here's the Sandia Mountains. These are, you can't quite see them there, the Ortiz over there. Here's the Cerrillos Hills, Cerro de la Cruz, and La Titia. So those are all volcanic features through here and even over here. And then you got Sandia, which is not a volcanic feature, but so I'm getting you ready to, we're gonna start talking about now the Rio Grande area and Sandias and stuff like that. So here's the Rio Grande River. It's over 1,900 miles long. Like I said, 475 miles are in the state of New Mexico. Over here, if you haven't been to the White Rock Overlook, it is spectacular. It is world class. And I'm not lying about that. So this is one of the views. There's all kinds of views in different directions, overlooking the Rio Grande Valley. And have you guys ever noticed in New Mexico how many things are called Black Mesa? It's like everywhere. It's like, where's Black Mesa? Well, what you have are these basalt flows, you know, and they kind of ooze out. If you picture like the Hawaiian Islands, these basalts, they just kind of, they're super hot, 1,000, 1,300 degrees centigrade, and they just gently flow along and they kind of create these cap rocks. So that's why there's black mesas everywhere. It's just this basalt associated with the Rio Grande Rift. And this is probably up near Pilar, yeah. Great birding if you go there. I don't know too much about where the water all goes because those are major issues, but only about 20% of the water makes it to the Gulf of Mexico. So we talked a little bit about this before. This is a better diagram. This is the Pacific Ocean over here, the West Coast, and you have the oceanic plate or crust dipping below. This is not to scale because that crust is only about a couple miles thick. And the continental crust is 10, 20 miles thick. So it's a very thin skin, really. And it gets pulled and goes underneath the continental crust. So it's the subducting plate here. And right in California, California has massive volcanics historically and all that. So you get a lot of stuff right by the coast. Well, eventually we get this mantle upwelling that's on the interior, the rift zone. And that's what caused our Rio Grande Rift and various mountains along the margin of that. So for us, this upwelling started showing its surface expression about 35 million years ago. So we had the laramide, the Rocky Mountains form about 50 million years ago. And then after that comes the rift. So first the pushing and the squeezing and then the cracking and then the molten lava comes up from the mantle. This map on the left, these are volcanic features, but these are basins tied into the Rio Grande Rift. So we didn't have this crack in the surface and you just had one big line. You kind of had these little pods and you had these little basins that weren't linked together. They had their own little river system or lakes in them. And eventually the river would kind of go from one to the next, but have a bunch of waterfalls. And then eventually it was all linked up together. So it was a long process to make the Rio Grande River. I think it's only been in its modern state for 500 to 300,000 years. So it started 35 million years ago, and as it is today, it's only been this way for a few 100,000 years. So that's nothing geologically, right? If you have Valley of Fire State Park, that's those volcanics down there about 5,000 years old only. If you go, this is a side note, but you go to El Malpais, they have some volcanics that are only 3,000 years old. But to my knowledge, those are probably the most recent volcanics in the state. And this is a little factoid. So in 1912, New Mexico became a state. And we became the land of enchantment. But the second choice was the volcanic state, the volcano state. We are a state loaded with volcanoes. I have never gone to look to see which state has the most volcanoes, but it may actually be New Mexico. Now, Hawaii is 100% volcanic, but I mean the most variety of volcanoes over time. And we'll get into some more details here with the Albuquerque Basin, but you had the Rio Grande Rift, and what you have is an asymmetric rift. So actually you had more uplift on one side of the rift, and then this the basin kind of fell downward here on the west side. So it's got major faulting on one side and less so on the other side. And then the Albuquerque Basin filled with sediments and basaltic volcanic type things. You know, it's 20, 30,000 feet thick. Oops, sorry. So here's a view. This is actually from my house. I live above the Bobcat Bight. So here's Interstate 25. And then here's all the sunlit hills. These are still the Rocky Mountains. This particular morning, it looks like El Dorado has a little bit of fog, which really helps us delineate the geology. Here's the Ortiz Mountains, the San Pedros. Down here's Sandia. And this is more or less the same thing, just kind of a bit of a close-up. So one Cerros Hill. Here's the Sandia Mountains, the Ortiz Mountains. Yeah, that's what I look at every night. It's tough. Moved here from Houston, and that's what I ended up with. All right, so back to the Sandias. So this is the granite, which is over 1 billion years old, that sets up. Now down there, it's more of a white granite. It's a slightly different granite than we have. But if you drive up the Sandias, you'll see there's that kind of pinkish, whitish granite everywhere. And that basin is loaded with all these rocks like we see at the surface everywhere else. They just kind of got buried because of all this faulting. They kind of shifted downward. And then they got filled up on the top here with the Santa Fe group, which is the rift filling. So when things pull apart, we call them a rift, kind of like your relationships. But this is a geologic rift. Fills in with layers of sediments and volcanic material. Here's an alluvial fan at the surface. Here's the Rio Grande River. And just about everybody in this room, I think, had been to the Grand Canyon. So one of the stops at the Grand Canyon highlights the great unconformity. And it's like where there's over 1 billion years of missing time. And geologists are like, where did it go? Because there's always deposits. It's not like life stopped working for 1 billion years. Things are always being deposited. They get deposited, they get eroded. But we have the great unconformity right here, down there in Albuquerque. We also have it on the way to Apache Canyon. So you leave the Rocky Mountains on I-25 and you go immediately into some more recent sediments, you know, the Permian sediments. So you go from 1-point-something billion years old to 300 million years ago. So the great unconformity really is found all around the area. Let's see what this says. So I'm just repeating. Sandia started forming 23 million years ago. I think their heyday was about 10 million years ago. There's 30,000 feet of displacement on this normal fault. So a normal fault is something just kind of drops down. I think we talked about the rest of that. So now let's move on to the Ortiz and San Pedro Mountains. Again, I'm talking about younger and younger things now. So here's the Surreal Hills. So I'm driving down from, let's say, Espanola into Santa Fe. And here you see the Surreal Hills on a rainy monsoon day. So there's several of them right there. And then to the right, Cerro Bonanza, just the biggest one there, on I-25 coming up from Albuquerque by that rest area. And then over here are the Ortiz Mountains. I'm probably somewhere in El Dorado area. So the whole complex is called the Ortiz Porphyry Belt. Porphyry means coarse-grained igneous rocks. So they're igneous rocks. I'm going to tell you they're volcanic, and we'll get to that. Igneous intrusions began around 36 to 28 million years ago. So what else was going on 35 million years ago? The onset of the Rio Grande Rift. So it's tied into that. All these things are kind of linked together. They just express themselves differently. And the rocks here are a little bit different. So that rift, remember we talked about the black mesa? So most of those are basalts, this kind of black mafic rock that comes out in sheets. But these are andesites named for the Andes. It's got, they're kind of more grayish colored, and this monzonite is kind of a pinkish color. So when you go down there, you'll start seeing kind of more grayish rocks when you're driving through Cerrillos towards Madrid. So how did they form this Ortiz Porphyry Belt? So this is the key word on this slide, is they are laccoliths, and this is a picture of it now. So when you have volcanics, the hot magma pushes up, and sometimes it comes to the surface as a volcano, but sometimes it gets trapped in these layers, and it builds a mound, and this is called a laccolith. And so the sedimentary rocks get tipped up around it, and then they kind of start to erode away. And when you're driving through here, if you can remember, if you go down towards Cerros, between Cerros and Madrid, you'll see some little hogbacks, some rocks that are kind of just standing up on end. And you probably, wow, those are really cool. I wish my house was right here, or at least that's what I think. And those are just these sedimentary rocks that pushed up around the volcanic feature. So just think of these as volcanic mushrooms, I suppose, but they're called laccoliths. And sometimes there's multiple layers, so it'll be called a Christmas tree laccolith. So here's the top of one of the Cerros hills. So that's kind of just this expression of that top of that laccolith that kind of pushed up into the sediments. So some other things to think of is there's geologic word is called a dike. So when you have an igneous intrusion that pushes up and it cuts through the rocks, perpendicular, kind of like how this neck is here. This isn't really a dike, but that's kind of how it would look. And a sill is when it squeezes between the layers. So this is a bit of a sill. The magma, the hot magma material squeezes between layers.
So those, like the example of the hogbacks in the Galisteo Basin, the magma never burst through. It never became a volcano, just pushed it up.
Well, I can't answer that. It could have been a volcano, but we just haven't found the ash flow with that. It could have eroded away. So there's some potential there could have been a volcanic at the surface. But more of it, less volcano and more of this trapped magma underneath the sediments. And then everybody likes to talk about the mining history of Cerros and the famous turquoise, which the next slide is coming up on. But I told you about, you guys been past Golden? Golden is named Golden for the gold mines. So here I'd read on the internet, 350,000 ounces of gold were recovered and 1 million ounces remain. So don't be surprised if somebody wants to come mine gold down there. And this is just a photo of some of the old buildings from that era here, the mining in the late 1800s. And then turquoise is a secondary mineral in the cracks, and we'll talk about that, I think, on the next slide. So here, let's step through this turquoise. So the word turquoise comes from the country of Turkey. It's European. So early Europe, Turkey stone. So that's where turquoise comes from, because there's turquoise, the stone, in Turkey. And so the oldest known mines, 700 to 900 million years before the Common Era, or since AD. And here's a diorama down in this wonderful trading post. If you haven't been to this Casa Grande trading post in Cerros, you must go. It's worth the $2 or $3 to go through the swinging doors. It's a lot of old mining implements, a lot of rocks and minerals, a lot of newspaper cuttings about the mining. But anyways, here they're showing the Native Americans with pit mines. So they were mining turquoise back then. So it's known to be the oldest mine in the United States or North America, and most active during Chaco time. And this Cerros turquoise has been found down in central Mexico. It's been found in Ohio. It's been found in California, and somewhere far north. Everywhere I travel in the United States, because I love Pecos, and since I volunteer there, I'm always looking for the trade routes connected to Pecos. And a couple of years ago, I went to Cheyenne, Wyoming, in their museum, and there was Pecos on the map. There was a trade route from Cheyenne to Pecos. So this Cerros turquoise made it up into the Northern Rockies too through these trade routes. Galena also mined in that area. In fact, if you go to the state park there, they don't even talk about turquoise. They talk about the lead. But the Native Americans used that for pottery glaze way back when. Interestingly enough, the Spanish explorers, they didn't care about turquoise. They were after gold and silver. So the mines out there started in the late 1800s here. So the railroads came through about 1880. So a lot of life really started to flourish after 1880, as I say there. And it's interesting, in the late 1800s, 1890s, earliest 1900s, turquoise was more valuable than gold. So there's a company called Tiffany, and Tiffany had this color called blue. I don't know how many people have Tiffany bags or boxes, the color. And so there's some Tiffany mines out here in Cerros, and they looked the world or wherever for mines of their color, and they found their exact color match in Cerros. So they started some mining there and shipping it back to wherever they made their jewelry back east, back in New York and all that. So turquoise here is a mineral that forms in arid regions. So like Persia, Turkey, South America, our desert Southwest, that's where you find turquoise. It's usually out in the desert. You usually have volcanic rocks of some sort. There's cracks, and then there's groundwater, and it dries out and it precipitates. And over time, you get this copper mineral, turquoise. And one other little thing, there's only 4 minerals that are named for their color, or the color is the same as their name. So can you think of a couple of them? Turquoise, right? Turquoise color, turquoise, copper, silver, and gold. Just giving you things to talk about when you have coffee or beer. That's kind of a neat little fact though, huh?
Yeah.
So you can, what minerals are named after their color or the same as their color? All right, well, we're wrapping up here. We're getting pretty young now. Now we're getting down to where we're sitting here. So over here is where we are. Here's the OAS buildings, the Caja del Rio Road. Caja del Rio is the box of the river, and it's a volcanic field that formed here about 14,000 or 14 million years ago to 40,000. So it's, I think I have this on the next slide. It's about 60 little volcanoes. I guess I have that coming further up. We're looking at the Jemez Mountains. Sorry, I got ahead of myself. So here's all the Jemez Mountains. Here's Chacoma Peak, etc. Here are the Jemez Mountains from this direction. And then down over here, this is the Caja, the little bit of volcanic. Sorry, I got ahead of myself there. Got to talk about the Jemez first. So here's the Jemez Mountains. Driving down from Española, you can see them there. You can see the Jemez Mountains everywhere. So when you come out of Taos driving south and you just make that one little turn as you're leaving town and the Rancho de Taos, voila, you see the Jemez. When you're down in Albuquerque, you see the Jemez. So I always think about Native Americans, how important that was. You could see those Jemez Mountains from multiple directions. So that spans, I don't know what that distance is, but that's probably over 100 miles that they could communicate, make signals, whatever, from these mountain peaks. Anyways, this is from Española. You can see the Jemez Mountains. Up here, my partner, Debbie, she's a big skier. So she's skiing one day and she sends me this. Here's the Jemez Mountains. That's how they look from afar. And then up close and personal, here's the Bandelier Tuff, driving towards Los Alamos or Bandelier. And the mountains over there get pretty high, 11,000 feet. So here's Bandelier National Monument. And there were multiple eruptions around 1 or so million years ago. And a type of volcanic is a rhyolite. That's a lighter colored one. It's high in silica, high in quartz. It's kind of pink, buff, white, orangish. And then pumice ash flow. So volcanoes blow up and you get ash and it falls down and kind of fuses together. That's pumice. So if you walk over here to some of these trails, you can actually, the Native Americans walk trenches through their trails. They're so soft. And at Bandelier, they dug the cavates out. That's that soft pumice rock. So those are all volcanic. And then Caja Catue National Monument in collaboration with Cocha de Pueblo. Some of us call it Tent Rocks. There's a thing on the news on Thursday why that place hasn't been open for 3 years either. So keep your eyes, figure out why that isn't open yet. But it's part of the Pajarito Plateau. So the volcanics kind of look similar. Maybe there's the same sort magma source. There's still kind of this pinkish white color, but they're actually 6.8 billion years old. So at Bandelier, that was younger. That was 1.2 million years. This Tent Rocks is just a little older. So stratigraphically, geologically, chronologically sits below it. And if you haven't walked through too many slot canyons in your life, that one is magical. It blows my mind that it's so close to Albuquerque, to have such a beautiful place close to a major city. So now we're going to talk a little bit about Valles Caldera. So if you look at it from a surface geological, this round part here is the crater. And there's a lot of re-emergent little volcanoes in there, obsidians and things like that. Here's Redondo Peak in the middle. And then how did that form? So you go to the top here. So first there were just some cracks and you got some magma going to the top and these kind of independent volcanoes. What does that say? 14 million years to 1.4 million years ago. So that would have been Tent Rocks, would have been, that volcanic stuff would have been one of these volcanoes. Then there's a collapse. You have so much activity, it just kind of collapses because it's so chewed up, so hot and all that, it collapses. And then you kind of get more infill, you fill it up. And then over time, this magma chamber built up with more energy. And so it kind of popped it up. So that's the genesis of the Valles Caldera area. And if you're driving, here's Highway 4. This is Jemez Springs. So, and then the Valles Caldera Preserve National Park unit is right in through here. Elk, beautiful place. Obsidian. So I know we're sitting in an archaeology building. So anybody who built tools around here with obsidian, it probably came from Valles Caldera. Beautiful view of the caldera. All these are independent kind of little volcanic features, either on the rim of that caldera or on the interior of that caldera. So I want to talk about one other thing. I mentioned that this could be called the volcano state. So this something geologists talk about on the left here, the Jemez lineament. And these are Cenozoic volcanoes in red. So they kind of start down here on the Arizona border. Then here's El Malpais National Monument, Mount Taylor, which in the 1970s was the largest mining of uranium in the world. You had a volcano come up and make contact with the sedimentary rocks, and uranium was kind of came out of that, precipitated out. Then here's the Valles Caldera, which we're talking about. Then you kind of skip the Pecos Wilderness area and our mountains. Then this is the Mora area, and then you go over here to the Raton Clayton, where Capulin National Monument is. It's the easternmost volcanic field in North America. Skipping a little off, this is the Taos Plateau, but it is related to it. So major lineament of volcanic activity, and this goes all the way back, 1 billion, 2 billion years old. So it's just an old weakness in the Earth's crust. And the Rio Grande River just kind of intersects all this. So Rio Grande is north-south. This lineament is from the southwest to the northeast. And the intersection of all that is the Valles Caldera, this massive, volcanic complex. And in the 1960s, when geophysics was in its heyday, it was very well studied. And you can see from the photography how easy it is to see and observe, in Google Earth or whatever. It set the precedent for a lot of volcanic knowledge around the world because it was so easy to see and all that. So if you visit volcanoes around the world and there's volcanologists, some of what they learned came from Valles Caldera. New Mexico is an amazing state, the oldest water well, the oldest mine, the best studied volcano, the best Office of Archaeological Studies, the best friends groups. So everybody always says, when is this volcano going to blow up again? Well, I have no idea. So let's step through that a little bit. The last eruption here was 4,000 years ago. Scientists think the next eruption might be 10,000 years. So on the southern southwest margin of the Valles Caldera, Jemez Springs, there's hot springs and all that. So they're not just hot because somebody's, cooking in the kitchen. They're hot because there's a deep magma chamber. So there's some activity down there underneath the Jemez. So let's look at when the explosions that happened in the past. So here we are, the star, and there's the dot. Valles Caldera, this is the range of the last time, at least what they've been able to measure with the ash flows. So this is how far that volcano kind of blew off. For scale, all of us, it looks like, are old enough to have lived through Mount St. Helens. I don't know about you, Shelby, but that's the extent of Mount St. Helens. One that everybody's worried about is the Yellowstone one, because look at how huge that thing was. And that's going to go again someday too. And then over here in California, Long Valley. So these are the super volcanoes in our Western United States. And this is interesting kind of volumetric of their ash. So just the visual with the cubes. Yellowstone, second most ash, Valles Caldera, right here. And then eventually you get down to this little peanut called Mount St. Helens. So I don't think we have to worry about it too much. We'll probably get warnings and all that, but it's sitting out there to happen someday. Okay, now we'll get back to where we are. La Titilla, driving south on 599. So we're kind of in our neck of woods where we're sitting today. Here's La Titilla here. And it's a volcanic plateau. So these are more recent, 5 million years to 2 million years ago. If you look out through the landscape for fun someday, just count the little peaks. They're everywhere. There's at least 60 of them right in this area. And here's a map I found on the internet or in a book. So it's called the Cerros del Rio Field. So it's kind of this whole pinkish area. It spans both. This is the Rio Grande coming through here. Kind of spans both sides of that. Sits on top of the Valles type stuff, the Jemez type stuff. So it's a lot of what we see in our landscape in Santa Fe as you look towards the sunset. So here's a great area everybody loves, Diablo Canyon. And it is like a great cross-section of looking at basalt. So here's a photo of Diablo Canyon, and here's another one, it's over there by the Rio Grande River. These are different basalt flows. And basalt, just by its chemistry and physics, when it cools many times, you get these columns. And so when you're driving around, you can see all these columns and they indicate different layers. So there's at least 3 different flows there, and I'm probably oversimplifying it. So go hike through Diablo Canyon, but not on a hot day because it's super hot in there with all that black rock. But it's like a cross-section of the volcanoes. Which if you go down to Albuquerque to Petroglyphs National Monument, they have the volcanic hike you can do. And when you do that 3-mile hike, one of them takes you right through the inside of a volcano. So do that in the wintertime. It is amazing. So just to wrap up, this is everything we've talked about. Everything you can see through your car window. There's not one of these things that, I mean, you can't see inside Diablo Canyon. You had to hike for that one, but the rest of them you see through your car window. So we stepped through a great amount of geology here just by driving around Santa Fe. It's an amazing geological place. And that's everything. I know we zipped through a lot, but here's a lot of reference guides, various books you can buy, or websites. And if you want my contact information, you can jot this down, you know, follow up with me, or if you want to go hike something or come out to Pecos or whatever, or just ask me a general question. I love talking about geology all the time. So I'm done here. I'll open it up to questions.
So any comments on the meteorite up by Ski Santa Fe and the shattered cones?
Okay, so that's as you're going up, there's the Wand Trail on the left, right?
Mhm.
You guys know where that is? And that's like a billion-year-old feature. So there's one expression of it there, maybe further up past Chamisa Trail. That's what you're talking about.
Right.
So I don't have any comments. I have read about it. And when you're doing that Wand Trail, you do see something that looks like a big brecciated conglomerate. So I don't have any comments. I've read about it, and that's what they think it might be, like a very old meteorite impact.
Right.
I thought you were going to ask me about the Glorieta meteorite, which is a very famous meteorite. I was in the museum in Vienna, and they have a great meteorite museum, and they had about 3 pieces of this Glorieta meteorite. So it's one of the most famous ones in the United States. And that impacted near Glorieta. And then around 1100 AD, the Nambe Pueblo, people from Nambe Pueblo observed something like that, and they went over there and picked up some pieces. So I'm not really answering your question. I don't know anything more than what you read,
Okay.
so.
Okay, okay. And La Bajada, what is that?
La Bajada, what is that? These are good questions. I don't really know, but you can see it's the edge of the, it's a fault line. And then as you're driving on the right-hand side, you can see it's the end of the basalt flows, the Black Mesa. So I think it's just a fault line that's been shifted down to a normal fault.
Mhm.
And I imagine the basalts flowed past that and they've been eroded.
What can you tell us about the Mogollon Rim? As you're driving north, you see this huge, it's like a cliff.
Now, this is a talk about Santa Fe, and that's in central Arizona, which is okay. No, that's okay. So I basically can't tell you anything I know about it, but I know it's this big high thing, and archaeologically it's significant, and geologically, I'm sorry, I can't say anything about it. I don't know if you know anything about the Mogollon, but you're talking about in Arizona, right?
Yeah.
But further south, down by the Gila Wilderness. Yeah, yeah. So I'm sorry, I'll have to research that and send me an email and we'll talk about it. I'll be happy to look into it, but I don't know that. Sorry.
A little bit about the Garden of the Gods area, right? Which is on 14 going toward Cerros.
Garden of the Gods.
It's
I thought you were going to tell me Colorado Springs.
no, they call it the Garden of the Gods also, right? In that little stretch between Lone Butte.
Oh, I think I mentioned that. Yeah, okay. I didn't realize they called it Garden of the Gods. So I talked about that over here, that laccolith. So that's where you've got the tipped up rocks, right? That's where you got the hogbacks, the vertical rocks.
Yeah, there's a whole bunch of interesting stuff.
Yeah, there's vertical rocks there, and then you have some Cretaceous there. I've been on a ranch over there. There's a lot of petrified wood and everything. But this is what you had this volcanic body push up this laccolith, and then there's the sedimentary rocks over. So you had these flat layers, and then the volcano pushed up through it, and they tipped them up on their side.
Right, and there's a lot of conglomerate and kind of soft conglomerate in that area.
There might be. That's just in whatever the sedimentary unit is. I think it's Cretaceous out there.
Okay.
So you'll find these conglomerates. You'll find a lot of petrified wood. If you've been to Ball Ranch, which is the BLM land, there's a lot of petrified wood there in the Cretaceous as well. I'm not answering your question very well, but it's just, you had the pre-existing sedimentary layers that got kind of pushed up on end from this volcanic feature. Yep. Other questions? Shelby taught me how to go straight from one slide to the other, but I'm still doing the old-fashioned way with the arrows.
You're doing great.
Other questions or thoughts? You guys are an easy group. Thanks for all the great questions about Arizona and this obscure like little meteorite impact, from a billion years ago, or it's pretty old, but yeah. I appreciate that. That was great. Well, anyways, thank you for your attention. Thank you for coming.